Hello. So it's nice to be here. Thanks for the introduction. I came to CWI for 3 months many years ago, and I still remember it. It was a lovely time, and I've visited since. And it gives me particular pleasure to talk to the control community. I'm from the formal methods, but I'm based in a department where Alessandro Abate is also based, and he's moved over from control towards formal verification. So there has been some crossover, and many of the applications that I've been working on for the past few years connect to control and involve policies because they involve neural networks, so they involve data-driven policies and components. And what I wanted to do is to give you an overview, a high-level overview of recent research, hoping that there will be some crossover and perhaps that we can identify some connections. So I'll start with the motivating example. I mean, these days, AI is making decisions for us. We know that this AI is often driven by neural networks. And of course, it has also been known since around 2013, 2014, that these neural networks are unstable. So they can be very easily manipulated. This is an example that I'm using because, of course, it is an example of a decision that's made in real time and it's made very fast. And because it is image recognition, this is not something that you would program in C or Java or even Python. You would like to design a neural network for this. So it's not just that they can be manipulated, but they can be attacked. They can be attacked physically. They can be attacked digitally or physically by actually putting a sticker on it. But it is a very difficult problem to design such a network, neural network, correctly. But for high stakes applications, and high stakes applications are, for example, autonomous driving or even ADAS support that is being introduced in cars nowadays, but also in many other applications. Financial recommendations, advice, these decisions can be made by AI read neural networks. And for those, we need provable guarantees on correctness. Now, the AI and machine learning community is still focused on performance, okay? So how fast can we do it and what kind of accuracy we could get, but it is not necessarily focused on correctness. And this is why I'm looking at it from the formal methods point of view and trying to develop techniques that you can actually use to provide safety assurance for AI and neural networks. Why? Well, I mean, I'm giving you this example, and I've mentioned that there are, many systems that actually use traffic sign recognition. This is actually mandated by the EU. Speed limiting, but a recent survey has discovered that many drivers actually switch them off, okay? Because they find them annoying, okay? They find them distracting, but sometimes they find them dangerous, okay? Because they don't work, okay? And this is what I hope, formal methods can bring in. And formal methods, and in particular, formal verification is a topic that I have been working on for probably more than 30 years now. And the idea is to prove correctness of software. And typically, we either derive a model of the software, or perhaps after we've devised the model, you can then generate software. So you build a model, which is a mathematical abstraction, and correctness comes down to proving theorems about this software, but proving those theorems can be done automatically by algorithms using what we know as model checkers. So these techniques can be automated. And of course, formal verification is not just for verification. There are many use cases, additional use cases, and in particular, there is also synthesis where you can synthesize either the correct model, either model or a policy, and the idea is that it is correct by construction. Okay, it could be optimal, but it is also correct with respect to some specification. So for some time now, I have been working on model checking for various kinds of systems. They can be extended with real-time information, like timed automata. In my case, they are mainly probabilistic. But most recently, I have been trying to develop these techniques for neural networks. And this is what I'm going to focus on here. Now, the outcome of the probabilistic model checking has, over the past 30 years, I mean, with the help of the community, okay, not just me, has shown that there are many use cases for formal verification. You can use it for protocol debugging. You can use it for protocol verification, that is proving correctness with respect to some specification. And this is an example of a protocol, secret sharing protocol, which we were able to verify automatically the authors proved by pencil and paper. You can also use it for prediction, and in this case, this is an example of a DNA origami folding example, and that is an example of a pacemaker, which actually happens to be a timed automaton, and you can also do model checking, but I'm showing you can do optimal controller synthesis using the same techniques that are developed for verification. So why are neural networks more difficult? Well, they are more difficult because they are black box, because they are high dimensional, and because they are nonlinear. And because of that nonlinearity, the training does not actually, because there is no global optimum, the training does not stop at a global optimum. You don't really know where the training stops. So even if you have methods to improve robustness, they tend to encourage robustness, not guarantee robustness. So the guarantees will be probabilistic, and for really high stakes applications, you may still want to do verification pre-deployment. And that verification would then provide provable guarantees for the specific context. It can provide certification, so you can have a component, your ADAS component, for example, certified. And in the long run, it can also allow you to synthesize systems or policies that are correct by construction. So what this talk is going to be about is a high-level overview where I look at applications, and some of them will include data-driven policies, possibly with use in control. Some may include probabilistic methods, others not. But I will start with a quick recap of adversarial robustness certification, and in particular, one particular method that we developed recently that somehow has been missed out by the community, and we have developed it, and it is being useful for some interesting use cases. So there will be links to papers. You can also ask me if you are interested in following up some questions. Right, so what is adversarial robustness? I mean, the idea of adversarial robustness is to be able to prove that if you take a neural network and you take an input, say a traffic sign, then if you manipulate that traffic sign by some noise, which could be adversarial, could be a manipulation of every pixel, could also be localized like a patch attack, the decision, okay, is not affected. It means in SAT-friendly notation there does not exist a point in the vicinity of this traffic sign, so similar to that traffic sign that classifies differently. Okay, that's the conventional understanding. So adversarial robustness is a very simple property. I'm using it for illustrative purposes. It is really clearly not sufficient for what we want to do if we want to derive optimal, say, data-driven decision policies, but it is very useful as an illustrative example. Now, what we want to do, we want to compute provable guarantees for a trained neural network. We want to compute that you cannot manipulate that image. So, however you manipulate that image in that vicinity of the traffic sign, you will not change the decision. But this is not the same as building defenses. So for some attacks, like physical attacks, you actually need defenses. There are also other methods that try to train networks to encourage robustness and provide probabilistic guarantees, for example, randomized smoothing. I'm not talking about that. I'm talking about something that you can use for certification pre-deployment. Okay, so what is neural network verification? Well, it's really, we take the formal verification problem from software verification, where I have a piece of code, I have a precondition, I have a postcondition, and I want to show for every input in the precondition, the postcondition is satisfied for the output. Okay, that's what I want to have. Now, but I have a neural network. In some sense, it's simpler than code because it's an input-output function. It doesn't have loops. But on the other hand, it works in real vector spaces. And that's where the complexity comes from. So what we tend to do is we tend to work with simple specifications. And simple means polyhedral, okay, polyhedral in the vector spaces. So for the input, it shouldn't be too difficult to convince you that either of these can be expressed as a polyhedral notation, okay, in a polyhedral notation. For output, it's a little bit more difficult because the output is, of course, the output is max arg. So in order to turn the output into a polyhedral specification, I'll be looking at the confidence gap, and specifically I'll be looking at the difference between the max arg and the next most likely output, and hoping and proving that the max arg actually gives me the ground truth, okay? But this is a way to turn these into polyhedral specification. Well, but because exact verification, as you can imagine, will be tractable if we talk about real high-dimensional neural networks, what we do is we tend to lower and upper bound just to focus on worst cases. Now, neural network verification typically proceeds forwards. So you have a neural network, you have the polyhedral input specification, and what you do is you bound the worst case for each layer and you propagate the bounds, and then you bound again upper bounds to compute some polyhedral specification on the output. Now, the problem of that is, as we know already from static analysis, the bounds widen, okay? So you may get very loose bounds on the output, but the vast majority of formal verification works on that basis. And there are methods that are exact. For example, they try to reduce verification to satisfiability, SMT problem. The most successful method is convex relaxation, which relaxes activations to linear bounds. And linear bounds are simplest to solve because all you have to do is to solve LP. Okay, and you can also retrieve completeness by combining linear relaxation with branch and bound. So convex relaxation are best performance, but these loose bands may be an issue. So what we have done, and if anyone here knows about model checking, for example, for safety would start and proceed backwards, would start with a set of unsafe states and proceed backwards and check whether the inputs are included in the pre-image, okay? For some reason, people have not done it until very recently in neural networks. So what we are focusing on is backward analysis. So we start with a polyhedral output, and then we want to compute the pre-image. We combine it, as you will see. You can actually try to compute the exact pre-image, but for high-dimensional networks, this is not scalable because it's highly exponential, so it will not scale. So what we will do is to actually approximate the input by, again, upper and lower bounding it. And in fact, okay, the method that we have will proceed backwards. So I have a pre and post. They are both polyhedral, but I start with post, and I want to bound the input by upper and lower bounding. So it's either an over-approximation of the input or an under-approximation of the input. And with our method, we compute a disjoint union of polytopes. And these polytopes are obtained by backward traversal and symbolic bounding of activation functions, and we can compute either an under-approximation or an over-approximation. On its own, this will not work very well, so we need to combine it with pre-image refinement, and I'll show you a little bit more. And there is also a lot of heuristic and optimization because we still have an exponential growth because this is done individually for each activation function. Okay, so what I can do is we have two methods of pre-image refinement. The refinement, okay, I can start with a single polytope, and I will then keep refining that polytope to ensure that the constraints are satisfied into a family of disjoint polytopes. And I can do it by splitting on a feature, which we call input splitting, okay? So with feature aligned. So that's one. This is a user selected choice. And the other one is ReLU-aligned cutting plane. Now, if you can see this ReLU with linear bounding, okay, I can split it into two linear, and they are both exact, okay? So in the limit, I will get exact, and that's what we are trying to get. Of course, I still have to handle the huge search space. I use heuristics to deal with the search space and the exponential growth of the constraints. Now, what I finish off with is a disjoint union of polytopes. I can then use volume estimation, and that volume estimation compared to, for example, the input can also give me a quantitative guarantee, okay? So if it is an under approximation, I get an absolute guarantee that anything in that under approximation is guaranteed to be correct. That's one thing. And the other thing, if I stop early, because the method is anytime, I end up with a quantitative proportion, coverage of the input. And in many cases, we know that 99% may be good enough. Okay, so what can this do? Well, this is the first method that scales to high-dimensional tasks, and in particular, infinity attack and patch attacks. And we have recently extended it to GTSRB. I think I'm not showing you here. I think this is on NIMList, but GTSRB has been recently extended. We actually had to do much more optimization. So that links to my motivational slide. But I've also mentioned that you can estimate the proportion of inputs. So I obtain a coverage by estimating the volume of the, if it is under approximation, this is useful information. And you can see that, there are some control reinforcement learning benchmarks, which are low dimensional. So we have also applied them to and NIST. And compared to verification, verification answers yes or no. But with this, I can provide, in cases where the answer is no, I can provide coverage estimates. So the answer may be no, but perhaps it's 99% coverage may be good enough for certification. And we have done, I think, more. So for reinforcement learning control benchmarks, backward reachability analysis is something that has been studied, and in particular there were symbolic methods that were used in that case, which suffer from an exponential growth of the constraints. But in our case, we compare favorably because we have optimization, so we have reduced the search space, we've optimized the search, and in addition, we can provide these quantitative guarantees. Now, this is both under approximation and over approximation. You can see for many cases, you can have a single polytope, covering the input. Right, okay, so that was a connection to reinforcement learning. But as I've mentioned, image analysis is not the only type of neural network that is used in autonomous decision making. We also have many decisions that are financial decisions. Financial trading, for example, it's real time, but also advice, financial advice, insurance advice, etc. Recommender systems. There is a whole class of recommender systems that are based on neural networks because the data is available. It's not image data, and it may be sometimes tabular data, but even it will also have history. Okay. Now, over history, what can also happen is that there will be factors that have affected the behavior, okay, of the system over time, but these factors have not been recorded in the data because the data is only recording a subset of the information. And this is known in Pearl's causality framework. And we know that we then have to work with some structural causality assumptions, and that's what we are doing in this case, where there may be some confounder which has not been recording in the data, for example, jet fuel price. Okay, jet fuel price will affect the airplane ticket price, but say the data set only contains this information, and it looks like the popularity of the conference has increased the airline ticket price. And that means that if you apply a policy which has not learned this about these causal correlations correctly, the decisions will be wrong. In a sense, they will not be optimal, and they will provide suboptimal information, for example, to the airline pricing strategy. So what we have applied in this case is a statistical method known as instrumental variables. And the instrumental variables are variables which influence the outcome, but only via the action. And they are also not correlated with the confounding factor. Okay, and what this is actually something that has to be user defined. So there has to be someone who understands the problem, can identify what the instrumental variable should be. And for this, we have worked with a technique known as double machine learning, which also uses neural networks because it works with two-stage regression. One stage is actually a neural network to provide initial fitting, but we also are able to show very strong convergence property. So in terms of square root of n, where n is the number of samples, and this is actually close to optimal for these types of problems. And to show you how this works, it works not just for low dimensional, but this is high dimensional and real world examples, say real world benchmark examples, where our method is here. So this is the error of the learned causal effect, which looks very good on here, and also the expected reward of the induced decision policy. So the induced decision policy includes the history information. You can see that this is actually high, and also for some of these examples has very low variance. Okay, so it's an attractive method, providing you know how to identify what is a good instrumental variable. Even if you have something that is a good instrumental variable, you have to assume independence. You have to assume no correlation with the noise, at least, for some time window. Otherwise, the information will be ambiguous. So there are a couple of extensions that I don't have time to discuss. We have recently extended to imitation learning, which learns from the expert. But with our causal framework, we can also consider aspects that the expert did not know. And we can also learn optimal policies for RL from linear temporal logic via converting linear temporal logic to limit deterministic BQ automata. And finally, what we also have in a paper to appear at ICHCAI is we have a method to learn formulas in probabilistic LTL from Markovian strategies extracted from the reinforcement learning MDPs, and you can use them to explain the policies, for example, to debug the policies or to explain the behavior of the policies. So this uses learning from positive and negative examples, and it uses learning as formulas of temporal logic, which are kind of, more explainable to humans than, say, trajectories, sometimes trajectories. Okay. Right, but I've also mentioned that, I've been working with probabilistic models and probabilistic model checking, so I would just say that there is also a whole extension of neural networks that we have been working on, which enables probabilistic verification because the models are probabilistic models rather than deterministic, but they are probabilistic not because the likelihood that the neural network returns with a decision is a probability. This works with a Bayesian probability which computes the uncertainty, can evaluate the uncertainty of the decision. So, for example, can detect out of distribution data. So what we are working with in this case is an extension of neural networks, which takes a neural network and rather than having weights defined as single values, these weights are random variables. They are considered as random variables. If you can provide prior information in the Bayesian sense, using these random variables, you can compute the posterior distribution, and the posterior distribution will allow you to compute a decision in the form of a probability vector. Okay, so not argmax, but a probability vector over the classes for, say, a classification problem. So that is the difference between deterministic neural networks and Bayesian neural networks. But in my case, what the problem, and you can also study adversarial robustness, what the problem I'm focusing on becomes is before I was worried, if there exists a point X which in the neighborhood which classifies differently. And of course, this neighborhood has uncountably many points. But in the Bayesian neural network, what I'm focusing on is the probability which is conditioned on the training data. That's the Bayesian approach provides me with. And I want to bound this probability by some small value. Okay, so rather than saying there does not exist a point Y which classifies differently, I want to be able to prove that the probability of such a point similar to X existing is very small. Okay, it's bounded by some small value epsilon. And you can then, if you apply Bayesian neural networks, you can use the methodologies that we have developed to certify them and certify them with probability bounds, which can be either statistical or actually guaranteed lower bounds, for example, guaranteed lower bounds on the probability, which can then be used to synthesize strategies, okay? They can be used to synthesize strategies that guarantee certain probabilistic outcomes. So in this case, I will not have time to show you how this works, but we have applied it to the Medmonist example. This is the pneumonia data set, which has been recently created to stimulate research in medical diagnosis, similarly to what neural MNIST has done for image recognition. And we show, for example, how you can compute decision safety. So these are lower bounds on the probability. So you can, for example, then, depending on the problem, you can decide, whether this is high enough or not, okay? But what you can also see is that our method does not scale to the largest of the pixel, the largest resolution here. So, you would get a decision which can guarantee the lower bound on the probability, but only for small images for now. We need a lot more work in this case. Right, so another example that I will mention for Bayesian neural networks is a conditional, it's a principled approach which incorporates conditional value at risk. And the idea is that this probability vector over classes averages the probabilities, and it may not be what you are most interested in. So from the point of view of the application, you may just be interested in looking at, say, the 5% of most adversarially unstable cases. And this is something that can be done using conditional value at risk, and this one has been combined with Bayesian neural network analysis. And it is parameterized by this value alpha. And you can also produce a visual representation where this would be a safety threshold. And if you are the perturbations, if the region obtained from the perturbations is below the safety threshold, that's fine. If it is not, that means you need to fix the problem. And you can see that for MNIST, we are below the safety threshold, but for fashion MNIST, for the larger alphas, we are not, okay? And again, as I said, this is parametric, so you can focus on 5% or 10% or 25%, depending on the application. Okay, right, the final thing that I wanted to, no, this is also another thing. So the Bayesian neural networks have also been used in the context of updating policies, updating controllers. So if you have a system here which learns, from the environment, you can use a Bayesian neural network, probabilistic network, which learns on that data set, and it will provide an update to the controller. And what this approach can also do is not just a single step inference, single step meaning, a single step via the neural network, but it can do iterated predictions in the sense of reach, avoid, computing the reach, avoid probabilities. So it's a probability of reaching some good green set while avoiding some obstacles. And what we were able to do is to evaluate the methodology, and this methodology just extends the computation of the lower and upper probability bounds to this iterative setting, and we plugged in some benchmark controllers, sub-benchmark controllers in here with various obstacles to show how this works. Right, and the final thing I wanted to mention is, okay, I've been talking about neural networks and neural networks used in, say, traffic sign recognitions, neural networks used in decision policies, which may be, trained on some historical tabular information. But most of the time, the systems that people are developing actually combine both conventional software with neural network components. So these neural network components can be used for, say, policies, decision policies, controllers, as in the previous examples, but they can also be used for perception. And this is the case in autonomous cars, okay? Because we know that neural networks actually far exceed, the power of conventional software on perception, because they can do pattern matching in parallel and they do it very fast. So what you want to do is you want to combine the power of neural networks with the guarantees, the guarantees that conventional software provides. So what we have developed is a model, and it is a concurrent stochastic game model, where agents in that model have perception implemented as a neural network, okay? So normally an agent will just input data, but in my case, this agent can only use that neural network. Now, because I have a neural network, and as we know, neural networks work in vector spaces, I am forced to have a continuous environment. So I have a game which is in a continuous arena. It can have, in our case, up to 2 agents, okay? Actually, for fully observable, you can have multiple agents. For partially observable, which we will need to restrict. Now, each agent uses a neural network, and the idea is that this neural network will extract some information from the environment. Now, this information could be traffic sign recognition, or it could be, like in this example, localization. But as I will show you later, there are other types of estimation. It could be estimation of the distance that they use in aircraft control, or we have an estimation of pedestrian intention, which is again a neural network, okay? So this agent has a neural network that observes the environment, so it inputs this continuous vector space information, but stores it as the learned discrete, because we work with classifiers in this case, learned discrete objects, which we call percepts, and they can be thought of as symbolic. So they can be thought of as living in conventional software, okay? So what such a concurrent stochastic game is, well, I have some finite state agents, local state, and percepts. This is the space of percepts. And the continuous environment, and agents can only use the learned perception function to access the environment. That's the restriction. And it's a concurrent game, so joint actions will update the state probabilistically, because it is a concurrent and stochastic game. Some actions will be stochastic. So just in here, the example is that, right, we have, but motion control for this car can result in, the car sometimes moving to another, to the neighboring grid cell, okay? So this is the idealized grid. This is a grid that you would train from data on localization. And that's what we have to work with. So in fact, from the point of view of the representation, we will work, and that's the connection to the beginning of this talk, we'll work with a pre-image, okay? The pre-image of the network, say exact, assume that you can compute it, will impose a decomposition of this environment into finitely many polytopes. If I assume that I have a classifier network, I'll obtain a decomposition into finitely many polytopes. This is the initial starting point for the analysis, and I can then execute the game on this. I may need to compute the intersections, further of the polytopes. But that's how it works roughly. So what we can do under the assumption of full observability and zero sum, we can do the discounted expected reward computation over the infinite horizon. We have to make some assumptions, but they are typical Borel assumptions, and you can compute the fixed point of minimax. The only complication is that the optimal value, which does exist for this type of problem, may not be finitely representable, but of course all the intermediate stages will be. It's only that the limit may not be finitely representable. But as I've mentioned, you can also set up value iteration in the conventional way, but because this is an uncountable problem, you cannot run value iteration with a conventional vector. You cannot use alpha vectors. You have to work with alpha functions. Instead of working with that, we exploit this decomposition structure, and we work with these polyhedral representations. So we rely on the pre-image computations, exact or approximate, and polytope representations because of restrictions of ReLU and LPs to solve zero-sum games at each stage. And that's an example of a synthesized policy, and that's the value function, which shows, I think, the value for I think this is just a straight regression problem without a neural network. Now, I want to add a neural network, and that immediately forces me into a partially observable situation, because the agent that can only perceive the environment through the neural network just cannot see the actual state, okay? So this is a partially observable game, which you can simplify to a POMDP if you only assume that you have one agent. So now, this is what the learned percepts are, assuming that my neural network is doing localization. And I can work in a conventional way, again, under standard assumptions with the belief space, as we know for POMDPs, and you can do analysis in this way. But what the interesting thing is, what can we do if you consider a game? Because a game is actually more appropriate as a model for many real-life applications. Just consider an autonomous car driving and a pedestrian, crossing the road. This is not an MGP because we have two active agents. Now, unfortunately, from the game theory, there are severe restrictions because of the infinite environment that we have to put on. And thanks to a Czech group who have worked with not neurosymbolic, but they've worked with partially observable stochastic games with discrete state spaces. They have identified a useful class, one-sided variant, and in our case, this is a subclass of hybrid state post-Gs. Why hybrid? Well, because I have a continuous environment, but the local state spaces of the agents are discrete, and in addition, they store the symbolic percepts, representation as discrete. Now I have one-sided because only one agent, a main agent, uses neural network as a perception. The other agent is fully informed, and this is not because this is the real situation. This is only because we want to prove correctness of that behavior in the worst case. So for the worst case, I need to have this fully informed agent. And I also consider the discounted infinite horizon reward. So, I mean, just to give you an example, it motivates this. I have a situation where I have an autonomous car and there's a pedestrian on the sidewalk, and what that car is using in this case is not a neural network that recognizes traffic signs. Okay, of course, it could be as well as a kind of parallel module. But in this case, I'm focusing on a neural network, and such neural networks have been developed, and they are trained from video data. And the idea is for these neural networks to then predict how likely the pedestrian is to cross the road, okay? And for the pedestrian, we want to consider the pedestrian fully informed because we want to understand the worst case, because we don't want the pedestrian to die, okay? But the goal then would be to synthesize a strategy. And notice what I'm given is I'm given a trained neural network for that autonomous car, and I want to synthesize a strategy for that car to minimize the likelihood of the crash. So that's what we do, and in this case, as an abstraction, you can consider the vehicle has speed as a local state. It observes this pedestrian intention, which is likely to cross, not likely to cross, and actions are acceleration. So it's acceleration, deceleration, hopefully, when it identifies the pedestrian likely to cross. And to pedestrian, well, there are actually more behaviors, but you can simplify it to just, okay, crossing or back, but it can also do nothing. And, synthesize just some policies. For this, we have developed a method for these partially observable concurrent stochastic games, which extends HSVI. This is heuristic search value iteration that was originally introduced by Horak for the post-G case, but for the discrete state spaces. But we, again, work with continuous state spaces and exploit a structure via the pre-image of the neural network. So we, again, utilize the pre-image in this case, and we work with, as I said, alpha functions, not alpha vectors, and they are piecewise continuous under the assumption of ReLU. And we also have an efficient online method, so computed for a given state, but computed after pre-computing the lower and upper bounds from HSVI, okay? And all you have to do in that case is to solve a single LP at each stage, which is not much, believe me. Right, what we've also done is we've worked with safe online planning, and there is a little bit more of that, safe online planning via shielding. This is in conventional POM-DPs, but it uses a data-driven trajectory predictor, so it fits with the theme of the talk. And it has been evaluated on the real data sets. And okay, so with this, you remember I told you that at the beginning I said, well, I've worked on this formal verification and there are so many use cases. Now, I haven't worked on this formal verification for neural networks for many years, but we also have some interesting use cases as examples. So for, efficient policy learning, dynamic conformal prediction, protocol verification, optimal controller synthesis without temporal logic, but in each case with provable guarantees. So I hope that some of this was kind of relevant and of interest to you, because the problems are very similar. So I will just finish with what we are missing in that. Okay. So before I was just assuming a trained neural network. That means that if I compute that there is no guarantee, you have to go back to the beginning. You have to repair the network, or you have to retrain the network. Okay. Ideally, what you would like to do is to learn, to learn a robust network. So we've done something there, but it's in computational learning theory, and it does not scale up to neural networks. It's only single half spaces at the moment. And another example I wanted to mention is, well, I think we've been working with stochastic concurrent games where agents behave strategically, but the failure problems we have focused on were adversarial robustness failures. But in fact, there could be strategic failures. So you can generalize from adversarial robustness to strategic robustness. So the question is my system robust to however the other agent plays? And in this case, we have looked at RLHF, reinforcement learning from humans, where unsurprisingly, it's very easy to show that these methods can be manipulated by agents misreporting the information. And then the kind of more interesting question is how you can actually ensure what mechanism you need in order to guarantee robustness against strategic behavior, strategic manipulation. Okay, so that's all I have. I just have some remarks, and I just need to show my credits. And of course, thanks to all the people in my group. And thank you for your attention.